A very good morning, Doctor. We are from Group 4. We will be presenting about influence of agitation speed and aeration rate on fermentation efficiency. Our group members are Farah Afika binti Muhammad, Chen Yit Seng Suwaizen, Muhammad Zafir Ikhwan bin Muhammad Jais, Nur Atira Natasha binti Abdul Qadir, Nur Hidayah Balkis binti Ahmad Sofi, and Pang Yok Hang. We have control, randomization and replication in this experimental design. The control is maintained by keeping pH, temperature and medium constant across all bioreactors to ensure any changes in fermentation efficiency are solely due to the treatment combination. Randomization ensures the unbiased allocation of treatments, and replication strengthens the reliability and statistical accuracy by repeating each treatment combination. In this experiment, the experimental unit is bioreactor. Bioreactors are chosen as they provide independent environments, hence ensuring the reliable results. The factors are agitation speed and aeration rate, and each tested at two levels, 100 rpm and 300 rpm for agitation, and 0.5 VVM and 2.0 VVM for aeration. The response variable is fermentation efficiency, which will measure the impact of these treatments. In this experiment, we employ two experimental designs, which are a completely randomized design, CRD, and a two-level factorial design.
The first experimental design employed in this case study was the completely randomized design, which considered two variables, agitation speed and aeration rate, for evaluating the effect on the fermentation efficiency. The design consists of two variables, where the agitation speed was set at level of 0, 100, 200 and 300 rpm, and the aeration rate of 0, 0.5, 1 and 2 VVM. Zero level act as a control in each variable. By combining this factor, four treatments were created, each representing a specific combination of agitation speed and aeration rate. To ensure accuracy and reliability, each treatment was replicated 3 times, resulting in 12 experimental runs. Then, randomization was applied to assign treatment for fermentation setup. This is done to minimize the effect of external variability and reducing bias. The response variable measured in this experiment was fermentation efficiency, which was assessed by various parameters such as product yield, microbial growth, and rate of substrate consumption. This design allows us to analyze both the individual and combined effect of agitation speed and aeration rate using statistical tool while maintaining high level of experimental control and statistical resolution.
Next, I will explain how to construct the CRD for this case. To construct CRD, the first step is to determine the number of runs or the total experiments and the levels of treatments, which is for agitation speed, we have 0, 100, 200 and 300 rpm. For aeration rate, we have 0, 0.5, 1.0 and 2.0 VVM. For the first step is using Excel. We need to create a column of experiments, agitation speed and aeration rates with and the last one is RAND functions. Next, after we tabulate the data in each columns, we need to use the equal RAND function in the random number column to generate the random values between 0 and 1 for each run. Once the random number are generated, we need to sort in the row in ascending or descending order based on the values to randomize the assignments of treatments. After sorting, the assignment treatments in the randomized order will be ensure no visible sequence patterns. This approach maintains the complete randomization, which is critical for integrity of the experiments. Additionally, ensuring the sufficient replications of the treatments and validating the randomization process enhance the reliability of the result. So the CRD conducted this way is straightforward and will be minimizing the bias, making it a robust choice for many experimental setups. I think that's all.
So here we have a two-level factorial design. A two-level factorial design is a structured experimental approach used to evaluate the effect of multiple factors on a response variable where each factor is tested at two levels, which is at a low level and a high level. This experimental design allows for systematic evaluation of the effect of two independent variables, which is agitation speed ranging from 100 to 300 rpm and aeration rate, which ranging from 0.5 to 2 ppm on a dependent variable, which is in this case is fermentation efficiency. We all know that in two-level factorial design, each factor is tested at two discrete levels. So in this experiment, we have two factors. One of the factor is agitation speed, which range from 100 rpm to 300 rpm. So in this case, we have the low level, which is 100 rpm, and high level, which is 300 rpm. And the second factor is aeration rate, which range from 0.5 ppm to 2 ppm, and in this case the low level will be 0.5 ppm and the high level will be 2 ppm. So in two-level factorial design, the design can be represented mathematically as 2 power of k, where k is the number of factors. So in this experiment we have two factors, so the k will be equals to 2, and 2 power of 2 we will get 4 runs, which means in this experiment we have to run 4 times, which we take A as agitation speed and B with aeration rate. So we had 4 runs, which A will be at low level and B at a high level. A at the low level and B also at a low level. A at a high level and B at a low level, and the last round will be A at a high level and B is also at a high level.
The table in the slide represents a two-level factorial design experiment that evaluates the effect of two independent factors, which is agitation speed and aeration rate. The design systematically varies these factors at two distinct levels, which is low and high, to observe their effects. The number of runs are calculated using the formula 2 power of k plus number of central points. Hence, the total number of runs would be 7 in this experiment. The runs order indicates the sequence in which the trials were conducted, and the standard order follows the predetermined sequence based on the factorial design matrix to maintain the experiment structure. Agitation speed is one of the factors tested at two levels, where 100 rpm as low level and 300 rpm as high level. The aeration rate is the second factor, tested at 0.5 ppm as low level and 2 ppm as high level. The table also includes a column with random values generated, which is used to assist with randomization of run order to reduce bias and possible replication of identical conditions to ensure reliability. This experiment follows a full factorial design to explore all possible combinations of two factors at their representative level, such as low-low, low-high, high-low, and high-high. Each of the columns represents an individual trial with a unique combination of factor level. Central point of agitation speed and aeration rate, which is 200 rpm and 1.5 ppm, is also replicated and tested. It can improve the accuracy and detect non-linearity of the result by confirming that observed effects are consistent across repeated trials. The result of two-level factorial design is used to analyze how each factor independently affects fermentation effect, efficiency, and investigate whether the effect of the one factor depends on the level of the other factor.
Alright, hi, now I'm going to be talking about the comparison between the two designs. So first criteria is the purpose. For two-level factorial design, is to analyze the impact of multiple factors and their interaction. However, for completely randomized design, which is CRD, is to determine treatment's effects in a homogeneous environment. Next is the replication. Two-level factorial design ensures that there is balance throughout the factorial combination. Meanwhile, CRD makes sure that replication depends on the number of treatments and units. Next, for the randomization. randomized combination of factors and levels for two-level factorial design, and randomized allocation of treatments to experimental units for CRD. Next, the next criteria is data analysis. For two-level factorial design, it requires tools like ANOVA to analyze main effects and interaction. Meanwhile, CRD requires basic statistical methods which suffice for analyzing treatment effects. Now I'm going to be talking about the advantages and disadvantages of CRD. Starting with the advantages is that it is known for its simplicity. It is easy to design, implement, and analyze mass amount of data, and therefore it is suitable for experiments with minimal variability in experimental units. Next is the randomization. It reduces selection bias by randomly assigning treatments. And next is the flexibility, where it can accommodate a wide range of treatment levels and combinations. And then next is the cost effective. It requires fewer resources as the design is straightforward, and it is very versatile as it is applicable for single factor experiments with multiple levels. Next is the disadvantages. So the first disadvantage is that it assumes homogeneity. The performance depends heavily on the assumption that experimental units are homogeneous. And next is the error control, as that it is sensitive to variations between experimental units, which may lead to increased error variance. Next is that it is not suitable for complex designs, as it is not ideal for experiments with more than one factors or interactive effects. Last but not least is the replication demands. It requires sufficient replication to ensure reliable results, increasing experimental costs for larger treatments. So next, I'll pass it on to the next presenter to present about the advantages and disadvantages of two-level factorial design.
Advantages and disadvantages of two-level factorial design. Advantages. First, efficient assessment of factor. A two-level factorial design allows a quick identification of main effects and interaction between factors using minimal experiment run. Second, cost and time efficiency. With the only two level per factor, it requires fewer experiments compared to a higher level factorial design, and it reduces resources. 3. Preliminary testing. Ideally, for screening studies to identify significant factor before moving to more complex design. 4. Balanced design. Ensure the factor combination are tested uniformly, enhancing the reliability of estimated effect. The fifth, simplify analysis. Straightforward data analyzed using statistical tools such as ANOVA. And going to the disadvantages, first, limited information. It only evaluate linear effect and cannot detect curvature or higher order interaction without center point of additional level. Second, assumption of linearity. Assuming that factor effect are linear between the two levels, which might oversimplify the real world scenario. The third, not suitable for complex system, insufficient for detailed optimization or system with significant non-linear interaction. The fourth, required balance level. Both high and low level must be carefully chosen, as inappropriate level can lead to misleading result. That's all.